Welcome back, pre-calculus. We're going to move on to lesson 2.1, example number 2. We're now looking at graphs of monomials that have negative exponents. So instead of having just x squared or x cubed, we're going to have something like x to the negative fifth or x to the negative 2. So negative exponents up there. And these are a little bit more foreign to us. We can think about them as rational functions. In other words, this is the same thing as negative 3 divided by 4x to the fifth. So we can kind of think of it as a rational function, but especially for example b here, where it's 3 over x squared, we're not used to having that squared or x to the fifth in the denominator. So I think we should start off by exploring these in Desmos. So negative 3 over 4x to the fifth. And I'm going to put that in here, negative 3 divided by 4x to the fifth. And let's see what that looks like. So it looks very much like our rational degree or a rational function with an odd degree, just like 1 over x or 1 over x cubed or 1 over x to the fifth, except for instead of being down here like we're used to seeing it, it's actually, and up here, it's been flipped. And that's because of the negative sign out front. So let's see, if we had just say negative 4x cubed, does that change anything? Well, it does when you put it there. Let's try this. Negative 4x cubed, nope. What if it was just negative 4x to the first power? Nope. See how everything's up there? Not, it pulls it away a little bit, but the shape of the graph is the same. So if we have an odd degree, and if I take away this negative function, negative piece of it, if we have an odd degree function, it's going to look like our regular reciprocal function that we're used to, right? And it doesn't matter if it's x cubed or x to the fifth or x to the seventh, it's this general shape, unless we put a negative sign out front. And when we put a negative sign out front, it flipped which quadrants it was in. Now let's go and look at what the even ones look like. This one's a little different, and I'm just going to make it a generic 1 divided by, and this time I'm going to do x squared. Look what happens there. And that interesting. So this piece that was down here on the negative side, once we square it, it ends up being on the top part in quadrant 2 instead of quadrant 3. And so it's almost creating, my students like to call it a volcano. And they call these graphs the whoosh whoosh graphs. So that would be anything like x squared. Does it change if we make it x to the fourth? Not a little bit, but the general shape of it is the same. We're still in quadrants 1 and 2. Same thing. So it doesn't matter about the degree. What happens when we put a negative in front of it? What do you think is going to happen? I think it's going to flip it below the x-axis, and that's exactly what it does. So if it's even degreed and it's positive, it's going to be in quadrants 1 and 2. And if it's even degreed and negative, it's going to be in quadrants 3 and 4. All right, so now that we've explored that, let's see if we can do these graphs. I think we can. All right, so for A, we said because it's negative, it's going to be in quadrants 1, sorry, that's 2 and 4. And it's going to look something like this. Again, is it a terribly precise graph? No, that's not what we're looking for. We just want the general shape of the graph. And they want us to come up with a domain again. For this domain, what's the one thing that x cannot be? X cannot be 0 because we have an asymptote there. So we're going to go from negative infinity to 0, and then from 0 to infinity. We also have a horizontal asymptote at y equals 0, so our range is also going to be negative infinity to 0 and 0 to infinity. All right, what about x and y intercepts? Are we going to have them for these monomial powered functions that are rationals? No, because of those asymptotes, we're going to have no x or y intercepts. All right. Next, it says end behavior. So what is the end behavior going to look like for this one as we go to negative infinity and to infinity? It's going to get close to that asymptote. And where did we say that asymptote was? Right there at 0. So for both negative infinity and positive infinity, the limit as x approaches those values is 0. It is not continuous on its entire domain because we have what kind of discontinuity? As I write continuous. We have a infinite discontinuity because we have an asymptote. And where is that asymptote at? That is at x equals 0. Okay, we've talked about in behavior range, domain range, intercepts, in behavior continuity, and then where are we increasing or decreasing? We are increasing, so from negative infinity to 0. As we read the graph left to right, always left to right, remember. Negative infinity to 0, and when we go over here, yeah, it's on the negative part of the graph, but as we go left to right, it's still increasing. So from 0 to infinity. Now this is this an even or an odd function? Well, this is an odd function. Why? Because it is symmetric about the origin. Good. All right, looking at B, when we explored this, we said if it is an even degreed rational function and it's got a positive leading coefficient, it looked something like that. The domain is the same, so negative infinity to 0. We still have an asymptote there at 0. But notice our range is different because we're only in quadrants 1 and 2. Our range is from 0 to infinity only. We don't have anything down in the negative portions for y's. Still no x or y intercepts because of our asymptotes. The limit as x approaches negative infinity, g of x is going to go towards that horizontal asymptote, which is at 0. Same thing for the limit as x approaches infinity of g of x. That is also 0. We have an infinite discontinuity where? Where's the one x value we can't have? Right there at our asymptote, and that is at x equals 0. And for this one, as we go left to right, we are increasing from negative infinity to 0. But are we increasing on the other side of the y-axis? No, on the other side of that y-axis, we start going down. So we're decreasing from 0 to infinity. And for this one, are we even or odd? We're an even function. Why is it even? Because we're symmetrical about the y-axis. All right, you pause your video here. You try. Come back when you think you have it. All right, welcome back. So we got h of x is equal to negative 1/2 x to the negative 4. Well, because it's an even function, it would normally be in quadrants 1 and 2, but that leading negative coefficient says it is going to be down in quadrants 3 and 4. Our domain will still be the same. It's going to be from negative infinity to 0, and then 0 to infinity. But instead of our range being from 0 to infinity, we're going to be from negative infinity to 0. Still no x or y intercepts because of our asymptotes. We have end behavior going to where? To those asymptotes. So the limit as we approach negative infinity is 0. The limit of h of x as x approaches infinity is also 0. For this one, as we go to left to right, we are decreasing and then we're increasing. So we're decreasing first this time, and that's on negative infinity to 0, and increasing on 0 to infinity. Is this an even function or an odd function? This is an even function. Why? Because we are symmetrical about the y-axis. All right, that's it for this example. Coming up next, we're going to look at rational exponents when our exponents are fractions.